Today is the fourth day of myself transacting the lesson Chemical Thermodynamics. It's a Tuesday, 16th of November 2021. Right now, in the previous class, I had completed till the application of first law of thermodynamics. Okay, and today I must explain you the second law of thermodynamics. Now, in order to explain the feasibility, the spontaneity of physical and chemical processes, a new law known as second law of thermodynamics has been formulated. The law introduces two new thermodynamic functions. So as soon as second law of thermodynamics comes to your mind, think about the two new functions, thermodynamic functions, namely entropy and free energy. Now this entropy and free energy have been used to explain the spontaneity of the process. So here in this chapter, in this part of the chapter, in the following subsections, we will first discuss the spontaneity. What is the meaning of spontaneity? What is the meaning of a spontaneous process? What is the meaning of non-spontaneous process and all? So moving further, spontaneous and non-spontaneous process. Now we'll move straight away to the definition of a spontaneous process. A process which proceeds of its own accord under of its own accord under given set of conditions without any outside assistance is called a spontaneous process. Okay, now they occur on their own accord. However, there are some processes which require initiation. They just have to be started, and then they start moving forward in the forward direction. Such processes, once initiated, proceed by themselves. For example, there is burning of coal in air. Okay, burning of coal is a spontaneous process, but it needs initiation. The coal burns only when a flame is brought near the coal. Similarly, the combination of hydrogen and oxygen gases to form water is a spontaneous process, but it is necessary to initiate the reaction by using an electric discharge, which results in the formation of water. So, we can say a spontaneous process is also called a natural process. It is a natural process. All spontaneous processes tend towards equilibrium and, as such, are irreversible. Now, examples, you can have a look at the examples. Some examples are dissolution of sugar or salt in water, melting of ice and evaporation of water, neutralization of sodium hydroxide by hydrochloric acid, okay, and then dissolution of zinc metal in copper sulfate solution, okay. Then we have on the next page diffusion of gases from a region of high concentration to a region of low concentration of the gases. Then 6 is osmosis. 7 is flow of heat from a body at high temperature to a body at low temperature. Then flow of water from a higher level to a lower level. So these are some natural spontaneous processes happening. Number B. Now have a look at some spontaneous processes which require initiation, like burning of coal. Coal burns only when it is set to fire. Number 2 is decomposition of calcium carbonate. Limestone decomposes only when it is heated to 1070 Kelvin. That is calcium carbonate. The third one is combination of methane and oxygen. Now, methane and oxygen react with each other only when this reaction mixture is ignited, it is heated. Okay. Then some features of spontaneous process. So, the spontaneous process, once initiated, occurs without any external assistance. Number 2, a spontaneous process is an irreversible process and occurs in one direction only. Okay, so these are the two important features of the spontaneous process. First two, then we have got the next one. Number 3, a spontaneous process always proceeds in the direction which leads to the attainment of equilibrium. So, with the initiation, irreversibility condition, and then leading to equilibrium. Okay, then number 4, time is no factor for a spontaneous change to occur. This change may occur slowly or rapidly. The number 5, a spontaneous process is accompanied by an increase in the disorder or randomness of the system. So this is entropy. So a spontaneous process, there is always an increase in the entropy of the system. So remember, entropy means degree of disorder or randomness in the system. Then moving further to non-spontaneous processes, definition: the processes which cannot proceed neither by themselves nor by initiation, they are generally called non-spontaneous processes. For example, transfer of water from a lower level to a higher level. We need a water pump. Okay. It is a non-spontaneous process because it cannot take place by itself and requires external effort in some form. In fact, a non-spontaneous process is always accompanied by some other process. Similarly, transfer of heat from a body at lower temperature to a body at higher temperature is also a non-spontaneous process. So, some other examples you can see. Number 1, examples of non-spontaneous process. That is, the first one is decomposition of water by electrolysis. So, if you don't pass current, water will not undergo electrolysis and decompose into hydrogen and oxygen gases. The next one is number 2, formation of ice in a refrigerator. A refrigerator would convert water into ice as long as the energy in the form of current is supplied to it. Okay, otherwise it will not convert water into ice. Okay. Then number B, spontaneity and the driving force for a spontaneous process. Generally, the tendency of a process to occur spontaneously is called spontaneity. Tendency. Spontaneity is what? A tendency of the process to occur spontaneously without the help of any external assistance on its own occurred. Now, in a given set of conditions, a chemical reaction proceeds spontaneously in a particular direction. The occurrence of the same reaction in the same set of conditions is not spontaneous in the opposite direction. Therefore, there must be a driving force which makes a chemical reaction spontaneous in a particular direction. So, here the force which is responsible for the spontaneity of a reaction, that is the force which makes a reaction spontaneous in a particular direction, it is called a driving force. So, we will discuss the criteria. We will discuss the will try to explore the different criteria for the spontaneous changes happening in a chemical reaction in the forthcoming section. So the first one, delta H, enthalpy change. Delta H stands for enthalpy change. This delta H stands for what? Enthalpy change. It stands for, remember, it is standing for enthalpy change. Delta H, we have seen already that a system has a natural urge to acquire the most stable state, which corresponds to the state of the minimum energy. An exothermic reaction proceeds with the evolution of heat. In an exothermic reaction, the enthalpy of products is like less than the enthalpy of the reactant. So remember this. In an exothermic reaction, the enthalpy of the products, the enthalpy of the what do you call products is less than that of the reactant. So this is an important point over here. You better mark it. In an exothermic reaction, the enthalpy, this enthalpy H only, the enthalpy of the products is less than the enthalpy of the reactant. That's why delta S is equal to H2 minus H1 or HP minus HR. Thus, the occurrence of an exothermic reaction means the transition of the system from a state of high energy to a state of low energy. This is in accordance to the law of nature. Hence, an exothermic reaction should proceed spontaneously. A large number of reactions, spontaneous chemical reactions, have been found to be exothermic. Like over here, reaction between hydrogen and oxygen to form water. It is an exothermic reaction, spontaneous, once initiated. Then combination of hydrogen and chlorine, okay, to form hydrogen chloride, spontaneous, exothermic. For exothermic change, there is a negative sign for delta H. Then combination of nitrogen and hydrogen by the Haber's process to give ammonia gas. That is also an exothermic spontaneous change. So, for an exothermic reaction, remember, for an exothermic reaction, always remember delta H is always negative. This is one sign condition you have to remember. For an exothermic change, reaction or a change, delta H, the change in enthalpy is always negative. That means delta H is equal to H2 minus H1 or HP minus H R, it is equal to negative value. Okay. Thus, chemical reactions having negative values of delta H should be feasible. Feasible means possible, and it should occur spontaneously. Moreover, negative value of delta H is not the only criteria of spontaneity. There are other criteria also. So let us have a look at that. Although a large number of spontaneous processes possess a negative value of delta H, yet it cannot be regarded as the only criterion of spontaneity. This criterion, however, is unable to explain the following facts. Okay, so this criterion means the negative value of delta H. Now, feasibility of endothermic reaction. There are endothermic reactions which are also possible. An endothermic reaction proceeds with the absorption of heat, plus sign for delta H. In an endothermic reaction, the enthalpy of a product is more than the reactants. Therefore, the occurrence of an endothermic reaction means the transition of system from a state of low energy, low enthalpy to a state of high energy, high enthalpy, which is against the law of nature. Moreover, for an endothermic reaction, delta H is positive. So remember this sentence. For an endothermic reaction, delta H is having a positive value. For an exothermic reaction, delta H has a negative value. So according to the above criterion which you have just now seen, an endothermic reaction should not occur at all. But this is not true. A large number of endothermic reactions are feasible and occur spontaneously. So in this chapter, in this part of the chapter, we are going to learn about the spontaneity for both exothermic as well as endothermic reactions. So there are a number of reactions like this ammonium chloride. If we add ammonium chloride in water, then you will find if you feel the solution which is being formed with your fingers, then you will find that there is some cooling effect because it is an endothermic reaction. It absorbs heat. Okay, that's why delta H for this reaction is plus 15.1 kilojoules. Similarly, calcium carbonate, okay, our decomposition. Here also it is requiring heat, so delta H is plus 177.8 kilojoules. Mercury oxide also, delta H is plus 90.8 kilojoules. Now, this implies that a decrease in enthalpy is not only the factor which governs the spontaneity of a reaction. Some other factors are also involved in it. First one is this one is attainment of equilibrium. If the decrease in enthalpy is the only criterion, an exothermic reaction should always get completed. But this is never true. In case of several exothermic reactions, many exothermic reactions, when carried out in a vessel closed container, attain a state of equilibrium and do not go to completion. So that is one factor. Okay. Next one is reversible nature of the reaction. There are many reactions in which forward and backward reactions occur simultaneously. That's a reversible reaction. This means that the reaction with a negative value of delta H and the reaction with a positive value of delta H, they occur simultaneously. Negative value and positive value, they are occurring simultaneously. The example is given, the reaction between hydrogen vapor and iodine vapor to form hydrogen iodide. Over here, the negative and the positive value of delta H indicate that the reaction is occurring in the forward and the backward direction simultaneously. Okay. Now, for this reaction, the forward reaction involves a decrease in enthalpy, whereas the backward reaction involves with the increase in the enthalpy. So, from this all discussion, it is clear that the decrease in enthalpy helps in the occurrence of a chemical reaction, but it cannot be regarded as the only criterion of spontaneity. So, randomness and spontaneity, let us discuss this. A spontaneous process is always followed by an increase in the disorder or randomness of the system. This can be understood with the help of this example, mixing of two gases. Look at this diagram. Before mixing, gases are filled orderly. Okay, before mixing, this cap is closed. It is closed C. Okay. Now, when you open this C, the gases will try to mix with each other. Okay, and then after mixing, randomness has been increased. Okay, randomness increases when the two gases mix up together. So that is over here called spontaneity during the mixing of two gases. Increase in the randomness of the system leads to the spontaneity happening in the process. Then the other one is melting of ice. This melting of ice also a spontaneous process and leads to an increase in the disorder or randomness of the system. When ice is kept open, the heat flows from the surrounding atmosphere, which is at a higher temperature, and then it melts into water. In ice, the water molecules are arranged in a highly ordered fashion. This order of water molecules disappears when it melts. This is because in liquid water, the molecules are generally free to move. They are free to move within the boundary of the liquid. Thus, melting of ice involves an increase in the disorder or randomness of the system. So, we have been seeing again and again for the spontaneity, the disorder or randomness of the system have to go hand in hand together. Then only the reaction can be termed to be spontaneous process. Then the other example is evaporation of water. Now, if you look at evaporation of water, in liquid water, water molecules are somewhat arranged and are confined to the boundary of the liquid. But when water is kept in an open container, naturally it undergoes evaporation spontaneously. Slowly, the molecules come out of the surface and dissipate into the atmosphere. Thus, they attain more freedom. So, this more freedom means what? Disorder randomness. So, consequently, the disorder or randomness also increases in the case of water evaporation. Then, spreading of ink, spreading of ink in water. If we look at a drop of ink, if we add a drop of ink, it's added to water contained in a beaker. Okay, if you look at this, water being added to a water, ink is added to water which is kept in a beaker. It spreads spontaneously throughout the water, and the whole solution becomes colored. The process involves over here an increase in the randomness. So this is also one condition over here for the spontaneity. Randomness or disorder both have to be together hand in hand so that the process is what we call spontaneous. Now we can conclude one thing over here, that a spontaneous process proceeds in a direction in which the randomness of or disorder of system increases. So hence an increase in the randomness will be regarded as the criterion for what? For the spontaneity of a process. So this is what you have to remember over here. Okay. So this is an important sentence over here. Hence an increase in the randomness may be regarded as a criterion for the spontaneity of the process. That is a very, very important thing. Okay. Now moving towards the statement for the second law of thermodynamics. There are a variety of statements. Okay. So we have already seen a spontaneous process is irreversible and involves an increase in the disorder of the system. It always tends towards equilibrium. If one intends to go against a spontaneous process, one must have to do some effort and spend energy in some form. Now, this is all governed by the second law of thermodynamics. Now, there are various statements given by different persons. The first one is called Kevin Planck statement, which states that it is impossible to construct a device or a machine which operating in a cyclic manner has the sole effect of extracting heat from a reservoir and performing an equivalent amount of that. Means it is impossible to construct a machine which can do 100% work. Okay, that is the one of the first statement from the second law of thermodynamics stated by Kevin Planck statement. Okay, now the other one is called Clausius statement. Now, according to Clausius, if you look at the other statement over here, according to Clausius, again it is acting as the same thing. It is meaning the same. It is impossible for a self-acting machine working in a cyclic process. So remember the word cyclic becomes important over here for the second law of thermodynamics. And unaided by an external agency to transfer heat from a body at lower temperature. So if there is a machine which is acting on its own, that machine cannot, you know, that machine until and unless it is unaided by an external agency, it cannot extract heat from a body at low temperature and transfer that heat to a body at higher temperature. So to do this, it is always important for us to provide an assistant to the self-acting machine. Okay, this was according to the next fellow, which is called Claudius statement. Then there are other statements also with regard to the second law of thermodynamics. All spontaneous processes are thermodynamically irreversible. That is number A under other statements. Number B, whenever a spontaneous process takes place, it is accompanied by an increase in the total entropy of the universe. That means there is an increase in the entropy. That means total disorder becomes high. Number C, it is impossible to convert heat completely into work, equivalent amount of work, without producing changes elsewhere. So all of them mean the same thing. So to just summarize all of this, I can say that according to the second law of thermodynamics, it is impossible to convert completely heat energy into work energy, equivalent amount of work energy, without producing changes anywhere. That means, or we can say, it is not possible for a machine which is acting self on its own to do work, to do work without extracting, without causing changes elsewhere. That means it has to be aided by some external force in order to do that work, which is like say transfer of heat from a body at low temperature to a body at high. That is something which is impossible, but that becomes possible only if we provide an external work or external support from outside. Okay. Now, based after this second law of thermodynamics, the statement over here, the word entropy. Let us try to understand entropy. We have already seen this entropy means degree of disorder or randomness in a system. So remember, a spontaneous change involves an increase in the randomness or disorder of the system. In fact, an increase in the randomness always favors the spontaneous process. So randomness and spontaneity, they are related directly to each other. Increase in one of them will increase the other also. Then now we'll come to some mathematical equations, mathematical relations with respect to this entropy. In order to measure the disorder or randomness of system, this thermodynamic function called entropy has been introduced by Claudius. Now, according to him, entropy of a system remains constant if it is not undergoing any physical or chemical change. But when heat flows into the system, the entropy of the system increases generally and vice versa. So remember this relation over here. Delta S means entropy change is equal to heat involved in the reversible process divided by the temperature, where Q reversible is heat supplied isothermally and reversibly to the system at temperature T. So please try to remember this formula. It will be required after some time. Delta S is equal to Q reversible by T. Okay. Then delta S is also equal to entropy of the final state minus entropy of the initial state, or this is products, entropy of the products minus entropy of reactants in the case of chemical reaction. So remember, the absolute entropy of a substance at 25 degrees Celsius and 1 atmospheric pressure is called the standard entropy of the system and is represented by S naught, S to the power of 0. This is pronounced as S naught, S naught. Entropy is also a state function. It is not a path function. Like internal energy and enthalpy, entropy is also a state function. Therefore, change in entropy delta S depends only upon the initial and final states of the system and not upon the path by which the system transits from the initial to the final state. Thus, we can say delta S is equal to del S final minus S initial, or for chemical reaction, delta S is equal to S products minus S reactant. So here, what is to be remembered? Entropy is a state function. It does not depend on the path through which the change is happening. Now, units of entropy. The change in entropy, that is delta, is an extensive property. Depends upon what? The number of moles of the substance, which we have already discussed right in the beginning of this chapter. So here, this much becomes important. Okay, try to remember this. It becomes important. The change in entropy, it is an extensive property. Why? What is an extensive property? It's a property which depends upon the number of moles of the substance present in the system, and it is generally expressed in the units joules per Kelvin per mole or calories per Kelvin per mole. Now, after this, what is the physical significance of entropy? Let us see. We already know entropy, it is a measure of randomness or disorder of a system. Greater the randomness, higher is the entropy of the system. For a given substance, the entropy of the system is minimum for the crystalline solid state, while it is maximum for the gaseous state. The liquid state possesses the intermediate value. So, with the knowledge about the entropy of a system, my dear boys, with the knowledge about the entropy of the system, it is possible to find out what is the state of the system. If we have a knowledge about the value of the entropy of the system, then we can estimate whether that substance is in the solid state, or whether it is in the liquid state, or whether it is in the gaseous state from the value of the entropy. Now, here entropy is also minimum. In the gaseous state, the constant particles are free to move in the space available to them. Thus, randomness is maximum for the gaseous state, and consequently, the entropy is maximum. So, if the entropy is highest, possibly the substance is in the gaseous state. If it is mediocre, it is possibly in the liquid state. If it is what you call minimum entropy, then we can talk about the substance being in the what you call solid state. Now, after that, here this comparison of the entropies for gas, liquid, and solid crystal is given. Okay, this one you try to remember. Okay, then entropy and spontaneity is of a process again over here. Since the increase in randomness always favors a spontaneous change, it may be thought that the process having positive value of delta S is feasible and occurs simultaneously. So this sentence you underline. This sentence you underline. Okay, and remember it. This one till here. Till here. Okay, till here. This you underline it. Increase in randomness always favors a spontaneous change. So we can say that a positive value of delta S, reactions which are having positive value of delta S, which is entropy change, are feasible and they occur spontaneously. Okay. Then let us consider some examples of where. Let us consider entropy change for the following systems. For isolated systems, here we can see in an isolated system, no exchange of matter or energy takes place between the system and the surrounding. Mixing of two gases, spreading of an ink droplet in a beaker filled with water, etc. as a system do not involve any change of matter energy. Now, over here, the spontaneous process occurring in an isolated system involves an increase in the disorder and hence an increase in the entropy of the system. Therefore, you can say that for spontaneous process occurring in isolated system, the entropy change of system is positive. So here, remember this. For spontaneous processes occurring in the isolated system, the entropy change of the system is positive. It is what? It is positive. Remember this. For spontaneous process occurring in the isolated system, the entropy change of the system is positive. So this can be asked in the multiple choice question. Positive, negative, neutral, zero, whatever. Okay, but you have to choose the correct option. That is for spontaneous process occurring in an isolated system, the entropy change is positive. Okay, that is there. After that, for open and closed system which are open, when the system is not isolated, it is open. It is either an open or a closed system. For example, cooling down a cup of tea, chemical reaction taking place in an open test tube, heating of water in a sealed metallic container are such systems. Such systems involve exchange of matter or energy or both with the surroundings. In such cases, we need to consider entropy changes of both the system and the surroundings. So thus the total energy of the system will be equal to the sum of the change in entropy of the system and in the surroundings. So for such situation, for open and closed system, delta S total, the total entropy change is equal to entropy change in the system plus entropy change in the surroundings. Now we know for a spontaneous process, delta S total will be positive. Therefore, delta S total must be, it is always equal to 0 in such situation. Okay. Then, from thermodynamic point of view, the system and the surroundings, we know if we add system and the surroundings, it is positive value. It will make the universe. Therefore, for a spontaneous change, the total energy, total change in entropy is equal to the change in entropy of the universe. Hence, it is following that delta S total is delta S system plus delta S surroundings is equal to delta S of the, because delta S of the system and delta S of the surrounding, it is called universe, which is also equal to greater than 0. Thus, again, remember this for objective questions. The entropy of the universe always increases during a spontaneous change and tends towards a maximum value. It tends towards a maximum value always. Okay. Then then a system attaining equilibrium, maximum value of entropy when it is in a state of equilibrium. This is quite logical also because all spontaneous processes proceed in the direction of equilibrium. So for a spontaneous processes which has attained equilibrium, remember delta S is 0. Delta S is what? It is 0. Remember this also. Okay. At equilibrium, delta S value is what? It is 0. Okay. So on all these basis, remember point 1, point 2 and point 3. If delta S total is positive, that is delta S is greater than 0, the process is spontaneous and is in the direction as mentioned. And after, if delta S is 0, it is in equilibrium. If delta S is negative, then the process is what? Non-spontaneous. It is what? It is non-spontaneous. This you have to remember. These 3 points is very, very important point. If delta S total is positive, it is spontaneous and it is happening in the direction as mentioned. If it is 0, then it is at equilibrium, the process equilibrium. If it is negative, then the process is non-spontaneous. Okay. Now, however, such a process will be spontaneous in the reverse direction. The third one. Okay. Then, as I've already told you that time, entropy changes of the universe in reversible and irreversible process. Let us just talk about entropy change of the universe in a reversible process. So remember this formula: delta S system is equal to Q by T. It is the system, okay, not the surrounding system is Q by T. But we know the entropy of the surroundings decreases because the surroundings lose the same amount of heat, that is Q. Hence, there is a negative value for the surroundings. For the system, it is positive. For the surrounding, it is negative. From the thermodynamic point of view, the system and surroundings constitute the universe. Hence, you can say delta S of the universe for a reversible process is equal to delta S system plus delta S surroundings. If we add this two, it is coming to 0. So, for this situation, for a reversible process, the entropy change of the universe is what? It is 0. Because delta S system is positive, delta S surrounding negative, so they cancel each other. Okay, you have to remember this. That is equation 6.40. Then moving further, this means that in a reversible isothermal process, there is no net change in entropy and the entropy of the universe remains constant. Okay. The number 2, entropy change of the universe in an irreversible process. Suppose a system maintained at a higher temperature T1 passes Q amount of heat irreversibly to its surroundings maintained at a lower temperature T2. Then what will happen? There will be a decrease in the system, entropy of the system. So delta S system becomes over here. What is happening? It is an irreversible process. So system is maintained at a higher temperature T1 and it is passing Q amount of heat irreversibly to the surrounding. So the system is giving heat. It is losing heat to the surrounding. That's why the value of the entropy change. There is a decrease in the entropy system. That's why delta S system becomes negative over here. Minus Q by T1. Now increase because the system is giving heat to the surrounding. What is happening? There is an increase in the entropy surrounding. That's why delta S surrounding is a positive value plus Q by T2. So if we look at the net entropy change again over here, there is a formula delta S surroundings for an individual process is equal to putting all the values of we get Q T1 minus T2 by T1 T2. Now remember, since temperature 1 is greater than temperature 2, T1 T2 is a positive value. Hence, delta S of the universe for an irreversible process is always greater than it is always it is always greater than 0. Okay. Thus, underline this sentence: the entropy of the universe increases in an irreversible process. Increases in an irreversible process. Very, very important point to underline. Okay. Now, since all spontaneous processes are irreversible, it follows that a spontaneous process is always accompanied by an increase in the entropy of the system. This is why entropy of the universe is tending towards the maximum day by day. As you are moving further, as you are getting older, the entropy of the universe is always increasing. Okay, so This is in accordance to the conclusion we derived earlier on the basis of increasing the disorder in spontaneous processes. Now, we'll come to some relationship between adiabatic change and entropy. So, remember this, delta S is Q reversible by T for a reversible process, and for an irreversible process, delta S is greater than Q irreversible by T. Okay. Now, in an adiabatic process, there is no heat change. So, we know Q is 0. So, this entire thing becomes 0 for a reversible process. So, the entropy change for an adiabatic process is 0, whereas for an irreversible process it is greater than 0 because this Q irreversible is not equal to 0. Okay. Then, thus, during an adiabatic change, the entropy of a system increases if the change is happening irreversibly, while it remains constant if the change is reversible. Okay. Then entropy changes in isothermal expansion of a gas. Now, here the gas is being expanded isothermally, constant temperature. Now, when the expansion of a gas is carried out under isothermal and reversible conditions, we already see that the internal energy of the system does not change, that is delta U is 0. From the first law of thermodynamics, we know the equation is delta U is equal to Q plus W. This delta U is 0 for an isothermal expansion of a gas reversibly. Okay. So we are having 0 is equal to Q plus W, or Q is equal to negative 1. The work done in the expansion of n moles of a gas from volume V1 to volume V2 at constant temperature T is given by this equation. W is negative 2.303 nRT log to the base 10 V2 by V1. This equation we have already seen earlier. Okay. And then we can put this value in this formula over here and get delta S is equal to Q by T, that is equal to minus W by T, and put the formula over here. So we get a formula over here, delta S is equal to this T and this T will cancel. We get minus sign is here. There is minus sign inside also. They will cancel each other and we get a positive sign. Delta S is equal to 2.303 nR log to the base 10 V2 by V1. So this equation 6.42 can be used to calculate the entropy change in isothermal and reversible expansion of a gas. Okay. So till here we will do for today. In the next class tomorrow probably, uh, I'll be proceeding further in this chapter where we'll be learning an important thing, that is entropy change in phase transformations. Whenever there is a phase transformation, that means from a solid state or a liquid state, what are the energy changes involved? Okay. So this I'll be doing in the next class tomorrow. So here with this I would like to end my class over here, but just hold on because I need to record the attendance also. Okay. Okay, your attendance is downloaded, and one more reminder is there. Those boys, those who have not yet submitted your practical and your project copies, please do it at the earliest. Okay, please do it at the earliest. To submit it, if you are far away from Kalimpong, then you may send it by post. Those who are in and around Kalimpong, you may come to the school personally, possibly on Saturdays, okay, or in the afternoon, and submit it, keep it on my table, okay, and take a picture of that copy, the name, the front cover, and then send it to me personally in the WhatsApp group, in my personal WhatsApp, okay. With this, thank you so much. Have a nice day.